Hello everyone, this is Mariam from ODDS Lab in University College Dublin, and here, together with my colleagues in Florida Tech, we came up with an idea for facilitating one of the challenges in design, decision making. The design of the system can be much more complicated and challenging if you have uncertainty in the system. Especially, most of the system consists of many subsystems that are connecting together as if the output of one system is the input for another. So all uncertainties together end up to a complicated output distribution of the uncertainty. Moreover, the input of the system also can have some degree of uncertainty, as if any slight change in the input can end up to drastic change in the output. To prevent this, the system should design for robustness. The term of error margin index, EMI, it is defined in the context of compromised decision support, CDSP, as a metric to control and determine the robustness. EMI actually is the distance of the mean of the distribution from the target of the design, let's say lower required limit in our case, which is normalized by a standard deviation of the system. It is mathematically proved that if EMI for that design is bigger than 1, the design is going to be robust. Most of the designs have more than one objectives, and we should consider the degree of robustness for all of these objectives, and also we should consider their deviation from the target. So there's going to be a trade-off between this deviation and the degree of robustness. The literature related to compromised decision support, CDSP, are well studied this dilemma. However, there's going to be a question here for us that if you remember, in the classic definition of EMI and the assumption for CDSP is that the output distributions follow normality. But we know that in many cases, in real practical cases, they are deviating from normality. So how are we going to address this? In our paper, we consider the median of the distribution instead of the mean value. And in the denominator term, instead of using the classic definition of the standard deviation, we're going to consider some distances between median and some quantiles, which I'm going to talk about this. In the previous slide, we saw the limits are based on and quantile based on the reliability index. So this question might be appear that is there any comprehensive index similar to EMI that can be applied for reliable design instead of robust design? For reliable design in literature, there are a lot of quantile-based approach which are based on beta, which is the probability of having the solution bigger or smaller than some target or limits. But all of these approach have the complexity of solving the optimization, actually constraint optimization problem, which can be very challenging for complex systems or sometimes impossible for multi-objectives. By introducing actually making benefit from goal programming and the concepts of the compromised decision, we are introducing a new term of ReMI, which is the distance of the median of the distribution from the target and the median of the distribution from the reliability threshold. In section 3.2 of our paper, we mathematically proved that for any design that have this index bigger than 1, we can claim that design is reliable. Here you can see the variation of the target actually is lower required limit in our definition for the ReMI. By increasing the lower required limit LRL, according to the definition for ReMI, the denominator becomes smaller. By decreasing the denominator, the term of ReMI gets smaller and smaller, as if from ReMI bigger than 1 goes to the ReMI smaller than 1. We mentioned that ReMI bigger than 1 means that the design is reliable, and ReMI smaller than 1 means that the design is not reliable. So here you can see the change of the reliable space. For the values of ReMI bigger than 1, we have all the space reliable and gets smaller and smaller up to vanishing it. Here is a test problem we used in our paper, which is the oscillating function detailed in section 4.1. We use Gaussian process GP to have the posterior of this distribution. We used 5 and 25 samples. By using 5 samples, which sounds that is not apparently enough, we were not able to capture the oscillation. The GPU was recognizing this oscillation as the noise. As you can see here, we end up with a smooth mean value and a wide confidence band. However, by increasing the number of the samples to 25, at the end, to some extent, we were able to capture these oscillations. Later on, we considered some uncertainty for the input variable and wanted to investigate how gonna be the output distribution using these two GP posterior. Here is the corresponding output distribution for the normal input distribution coming from both GP posteriors. For the case of the 5 training samples, you can see here the GP posterior mean value is actually close to linear, so the output distribution is very close to normal as well. However, for the case that we have 25 and we were able to capture the true functions variation, the output distribution considerably deviates from normality. So the same normal input distribution, but ended up with 2 different output distribution. Here we calculated the admissible design space for reliable and robust design by calculating their EMI and ReMI for all design points, and also we calculated the deviation from the target for both design scenarios. And we noticed that the minimum of deviation terms for robust and reliable design happens in an identical solution if we consider some conditions. We can see the values in the table 1. Actually, in the lemma 1 in the paper, we mathematically prove that we can have the best possible reliable design and best possible robust design identical if we satisfy some conditions. For the next GP posterior, when we had the output distribution different from normal distribution, we can see that the deviation from target for most of the design scenarios behave differently, as if their minimum values happens in different design spaces. However, we can see that the admissible design space for reliable and robust design almost identical. In lemma 2 and lemma 3 of the paper, we mathematically prove that we can guarantee robust design if we have ReMI bigger than 1, meaning that having the both reliable and robust design at the same time if we satisfy some condition. Here I want to demonstrate my claim that I mentioned that wherever that I have ReMI values bigger than 1, the design is reliable for the desired reliability index, and wherever that ReMI term is smaller than 1, the design is not reliable. So I take one of the design points in the area that ReMI is smaller than 1, and I calculate the reliability index for the target of fx equal 2, which is the desired target. So I can see that this calculated reliability index is smaller than the desired one, so then the design is not reliable. And I take another sample from the area that the ReMI value is bigger than 1, and I calculate the reliability index here, which is equal to the desired reliability index, that meaning the design is reliable. At the end, we introduce a holistic dimensionless metric which, having that bigger than 1, can certify the stakeholder to achieve the desired level of reliability for complex, skewed, and non-normal output distribution. They don't need to solve complex optimization problem. They can simply calculate ReMI values for all design points and decide about their reliability. And the good news that it is applicable for multi-objective problems as well. And if they can satisfy some condition we introduce in the paper, they can have reliable and robust design at once. Thank you, everyone. I hope it was beneficial for you. If you have any question, don't hesitate to reach me.